Let me start with introducing some standard notation. I will denote by this calligraphic K the collection of all convex bodies in Rn, that is convex compact sets with non-empty interior. And in fact, in this talk, I will always assume that the origin lies in the interior of K. I'll denote by h of k the corresponding support function of the convex body K, that is just the width of K in a given direction theta. And this definition naturally extends to a one homogeneous function defined on the entire Rn. I'll denote by n the unit outer normal at a boundary point, which by convexity we know exists almost everywhere. And I will denote, this is important, I'll denote by S of K the so-called surface area measure of K. So this is a measure which lives on the unit sphere. And how do you define it? Well, you just take the usual n-1 dimensional Hausdorff measure on the boundary of K, and you push it forward via the Gauss map to the unit sphere. Okay. I'll denote the Lebesgue measure on the unit sphere by M. And finally, I'll denote by this K2 plus, the class of C2 smooth convex bodies with strictly positive curvature. So kappa is going to denote the Gauss curvature, just the determinant of the second fundamental form. And under these assumptions, then you can just calculate what is the Jacobian of this Gauss map. And you will see that in this case, the surface area measure always has a density with respect to Lebesgue. And this density is given by this determinant of this positive definite tensor, which I denote here by d squared of the support function. So what is this? There are two equivalent ways to define it. So for instance, if you like taking derivatives using the flat connection on Rn, so this is just the usual second derivative in Rn, but remember the support function is one homogeneous. So in the radial direction, the second derivative is of course 0. So you want to be perpendicular to those trivial directions. So you just restrict to the tangent space of the sphere. Completely equivalently, if you prefer to take derivatives on the sphere itself, so you have to take the second covariant derivative of the support function with respect to the spherical connection. But then since the sphere has curvature equal to 1, you have to add back in the support function times the identity. Okay, so these are equivalent definitions of this tensor, positive definite tensor. The only thing I'll need for the maybe for the sequel is another remark, is that this density, this determinant of the d squared of the support function is equal to the reciprocal of the Gauss curvature. That's again very easy to see from the calculation. Okay. Good. So starting point of this talk is a famous problem posed by Minkowski and solved by Minkowski and Alexandrov, which is to characterize all measures mu on the unit sphere, which arise as the surface area measure of some convex body K. And if the right-hand side, the measure has a density with respect to Lebesgue, and if this K is C2 smooth and strictly positively curved, then you just compare densities. And this amounts to the classical Monge-Amp pair PDE, where the determinant of this second derivative has to be equal to the given density F. So the three natural questions to ask is that of existence, when does such a convex body exist? And it was shown by Minkowski and Alexandrov that this happens if and only if two conditions hold. First of all, the barycenter of your measure mu has to be at the origin. And secondly, mu should not be concentrated on any hemisphere. Okay, so that takes care of existence. What about uniqueness to this problem? When is such a body unique? Well, by unique here, I mean, of course, up to translation, because when you translate convex body K, nothing happens to the surface area measure. So uniqueness up to translation actually follows from the equality conditions in the celebrated Brunn Minkowski inequality, which is written here. So this inequality holds with equality if and only if L is a homothetic copy of K. So knowing that the equality conditions are characterized in such a manner, then it's easy to show that you have uniqueness up to translation for this problem. And the last question, which I will not talk about, is that of regularity. Let me just mention that, as is well known, this problem of Minkowski really served as a great impetus and catalyst for the development of the theory of fully nonlinear elliptic PDE. And nowadays, I think it's fair to say that regularity is well understood. Okay, So our next topic is that in the 60s, Fiery proposed to extend the Brunn Minkowski summation the Minkowski summation operation as follows. So what is Minkowski summation? This is just the pointwise addition of sets, maybe with coefficients a and b here. Okay, but the nice thing about this operation is that on the level of support functions, it's immediate to see that actually you're just linearly adding the support function. Okay, so Fiery proposed, instead of using a little L1 combination of the support functions, let's use little LP combination here when P is larger than 1. Because when P is larger than 1, you'll see that this is still a one homogeneous convex function. So it must be the support function of some convex body. And this convex body he called the LP Minkowski sum of K and L. Okay, and indeed he established the corresponding LP Brunn Minkowski inequality, which is this inequality. Instead of taking the nth root now, you raise the volume of the LP combination to the power of P over N. And again, you have equality, but now you have equality if and only if, since P, let's say, is assumed to be strictly larger than 1, then you've ruled out translations, because now translations don't commute well with this new operation of LP Minkowski sum. So now that you've ruled out translations, you have equality if and only if L is just a dilated copy of K. Okay. And actually, there's nothing really new here. It's not like you get a new inequality. This is just a consequence of the classical Brunn Minkowski inequality together with an application of Jensen's inequality. Okay. Good. So in the 90s, Erwin Lutwak proposed to significantly develop the corresponding LP Brunn Minkowski theory. So for example, just as the usual surface area measure arises as the first variation of volume with respect to Minkowski addition, Lutwak asked, well, what is the first variation of volume with respect to LP Minkowski addition? And if you perform the calculation, you will see that this is governed by this measure, which he called the LP surface area measure, and I denote this by SP of K. And if you make the calculation, you will see that this is nothing else but the usual surface area measure times an additional term here, which is given by the support function raised to the power of 1 minus P. And indeed, when you set P equals 1, this corresponds to the classical case, you get back the usual surface area measure. Okay. So the next question, the natural question posed by Lutwak is what the LP Minkowski problem, that is to characterize all measures mu on the unit sphere which arise as the LP surface area measure of some convex body K. Okay, and on the level of densities, the corresponding PDE is very similar to what we had before, only now you have this additional nonlinear factor. Okay. So what is known about this problem? Basically everything. So when P is larger than 1 and the measure mu is even, this really simplifies the analysis to assume that the measure is origin symmetric, it's even. Then the existence was shown by Lutwak and Lutwak-Yang Zheng. And this was extended to general measures mu without this evenness assumption by an important work by Chu and Wang. And then the condition is when P is strictly larger than 1, that this happens if and only if the measure is not concentrated on hemispheres as we saw before. But now you don't need this assumption about the barycenter being at 0 because we've ruled out translations. Okay. So this is existence. Uniqueness, again, now no translations are needed. Again, this is automatic from the equality conditions in Fiery's LP Brunn Minkowski inequality that we mentioned. And of course, let me just remark that if the measure mu here is even, then uniqueness automatically will tell you that the resulting convex body, the unique convex body, will itself be origin symmetric, will also be even. So let me use this opportunity to denote the class K sub E, which is the class of origin symmetric convex bodies. Okay, so this E just stands for even. Anytime you see an E, something is even, something is origin symmetric. Okay. So now, let me try to convince you that this problem, this LP Minkowski problem, is also natural, not just for P larger than 1, but actually for P smaller than 1. And in particular, the case P equals 0 is very interesting. One reason for this is that the L0 surface area measure which is, maybe let me just change normalization and divide by the dimension. Then this is the so-called cone volume measure, V of K. How is this measure obtained? So instead of taking the n-1 surface area element on the boundary of K and using the Gauss map to push forward onto the sphere, what you do is you take this volume element, but now you take a look at the n-dimensional infinitesimal cone, which is spanned by this element together with the origin. Okay, and now you take this guy and push that onto the unit sphere. So in particular, what you will see is that you get a measure whose total mass is equal to the volume of K, not to the surface area of K, okay, as we had before. So really, this measure is very natural and really appears in many applications. So that's one reason to like the case P equals 0. Another reason is another work of Fiery from the 70s, who asked, what is the ultimate shape of a worn stone? So basically, imagine that you're walking on the beach and you see a nice stone, a nice pebble, and the waves are hitting the pebble. Let's assume that the waves are hitting it from every direction with equal likelihood. This is called the isotropic case. And Fiery tried to figure out what is the evolution equation which governs how the stone is going to be eroded until it reaches a single point. Okay, so obviously the change in time of the location x will be governed, will go in the direction of the inward normal, right? So minus normal, but at which rate? So of course, at places where the stone is more positively curved, it's going to be eroded faster. So let's assume that the erosion happens proportionally to the Gauss curvature, the Gaussian curvature kappa. Okay, so this is called the isotropic Gauss curvature flow. So at the time, Fiery did not know to justify the existence of short or long-term time existence of this PD, but nowadays this is well known, and it's known that there exists a maximal time interval along which everything is well posed. And this time interval is this maximal time is exactly the time when when the shape converges to volume 0. Okay, so this thing really shrinks until it reaches volume 0. But Fiery let's assume that this is well posed. So what would be the limiting shape as this thing shrinks to 0? Well, of course, it's going to be governed by self-similar solutions to this equation. So location x has to be proportional to the rate of change. Okay, so let's solve this equation, right? Let's take this self-similar solution and solve it. So let's dualize. So this means just take scalar product with the outer normal. So if you take a scalar product of location with the outer normal, just by definition, you're going to get the support function on the left side. And if you use our geometric evolution equation and take the scalar product with the normal, well, normal scalar product with the normal is 1, you're just going to get constant times the Gauss curvature. But remember, the Gauss curvature is 1 over the determinant of our tensor. So this is our equation. Let's move the denominator to the left-hand side and divide by n. This is just normalization. So you'll see immediately that the equation that you get is that the density of the cone volume measure will be equal to a constant. Okay, so this means that self-similar solutions exactly coincide with solutions to the question of for which convex bodies is the cone volume measure just a multiple of Lebesgue. Okay, and indeed, Fiery showed that whenever the convex body is assumed to be origin-symmetric, then necessarily K has to be a Euclidean ball. There are no other solutions, which means that this thing, his stone really erodes as it evaporates to a single point. It's the limiting shape. It does that as a Euclidean ball. Okay, no matter which shape you start. Okay. So indeed, Fiery's PDE was very influential, and it has been extended throughout the years in at least 2 different directions by many, many people. One generalization that you could study is to, instead of assuming that the waves hit the stone with equal likelihood from all directions, maybe you have some anisotropic potential rho. Okay, so this is called the anisotropic flow. And a second generalization is, instead of assuming that you're proportional to the Gauss curvature, maybe you're proportional to some positive power alpha of the Gauss curvature. Okay, so this is called the anisotropic power of Gauss curvature flow. And again, if you want to know how does this equation, converge to its down to a single point, the self-similar solutions, if you just repeat the very simple exercise that I solved for us in the previous slide, you're going to see that self-similar solutions are exactly characterized as solving the LP Minkowski problem. The LP surface area of the limiting shape K will have to be equal to the anisotropic potential times Lebesgue. But for which value of P? So P and alpha are related by this formula. And you immediately see that whenever alpha is strictly positive, this corresponds to P being strictly smaller than 1. So indeed, P strictly smaller than 1 is very natural in this sense. And also the uniqueness question is very natural because if you establish uniqueness for this equation, then you know exactly how this thing will shrink down to a point. Okay? Any questions? Okay, so can you still hear me? Yeah, okay, great. Okay, so now I hope I've convinced you that uniqueness question is natural, but already let me tell you that it's impossible to hope that you have a uniqueness for all p's smaller than 1, because this problem has a critical exponent given by minus n. The reason is that the density of the L minus n surface area measure is the so-called centro-affine Gauss curvature. It's called this way because it commutes nicely with, say, volume-preserving linear transformation. It has this very nice commutation property. Here, you want to find some linear map which acts from the sphere to itself. So really, you have no choice but to make it zero homogeneous, right? So this is this T naught notation. You make your linear map zero homogeneous, and now it acts from the sphere to itself. That's the commutation relation. So in particular, if you start with the Euclidean ball here, for which the density is, of course, constant, this T naught will just not, it's a constant density, so T naught doesn't do anything. It will remain constant. So this means that the centro-affine Gauss curvature of any ellipsoid will always just be proportional to Lebesgue measure. It will only depend on the volume of your ellipsoid. So this means that even for the family of ellipsoid, there's no uniqueness, right? All of the ellipsoids with the same volume will give you the same answer. So uniqueness is out of the question. For completeness, let me just mention that indeed Calabi in the 70s has shown that the only solution to this equation are given by ellipsoid. Okay, so P equals minus n is out of the question. However, what about the, above the critical exponent? This is called the subcritical regime. What about when P is below 1 but above the critical exponent? Many people have studied this uniqueness question when the right-hand side is Lebesgue measure. For example, there's a work by Andrews, Guan, and Ni, who established this uniqueness in this range of P's for origin-symmetric bodies. But the definitive result, the best possible result, was obtained a few years ago in this ACTA paper by Brendle Choi and Daskalopoulos, and they showed that for any K, no origin symmetry assumptions needed. Just let's assume that the origin lies in the interior of K. The only solutions to this equation are given by Euclidean ball. Okay. So when the right-hand side is the Lebesgue measure, you have uniqueness in the entire subcritical regime. This is the isotropic case. But what about other situations? What about if the right-hand side is not Lebesgue measure? Well, in general, you cannot hope to have uniqueness in the LP Minkowski problem in the subcritical range. Many authors have constructed counter examples, including our own Alina. So this means that for any P in this range, you can actually find two different convex bodies having the same LP surface area measure. However, if you fix one of the bodies, if you fix the right-hand side, certainly uniqueness can hold, right? We just for below 1, right? So, for example, we just seen that the Brendle Choi Daskalopoulos theorem tells us that for Euclidean balls, and in fact, you can extend the results to ellipsoids, you can have uniqueness all the way down to minus n. Okay, so this uniqueness question does make sense after all. So the next question would be, well, maybe can you have uniqueness in the entire subcritical regime? In fact, maybe even beyond the subcritical regime for other convex bodies, which are non-ellipsoids? That's a very natural question. However, unfortunately, the answer is no. It turns out that for any smooth body which is not an ellipsoid, you you can never reach the critical exponent. So in other words, this pk where uniqueness stops holding is strictly above minus n, and all the way, so and it's and the remaining range above minus n but before pk, you can use this non-ellipsoid, you can use your given body k, which is not an ellipsoid, as a counterexample to the LP Minkowski problem. Okay, so in this sense, this is a precise converse to the Brendle Choi Daskalopoulos theorem, and this characterizes ellipsoids. So ellipsoids are the only origin-symmetric convex bodies for which you have uniqueness in the even LP Minkowski problem all the way down to the critical exponent. For any body which is not an ellipsoid, this would not hold. Okay, so that's one thing you can do. Another thing is an observation that all of the counterexamples below 1 but above 0 that people have constructed were never origin symmetric. Okay. However, as soon as you cross 0, as soon as p is below 0, you can construct counterexamples. You can find two different origin symmetric convex bodies having the same LP surface area measure. So something happens at p equals 0 with origin symmetry, right? So now we've reached the celebrated and very influential conjecture of Borodsky, Lutwak, Yang, and Zhang, the even log-Minkowski conjecture, which predicts that for any p in this range from 0 to 1, uniqueness should hold in the even LP Minkowski problem. Now, many of you probably know this conjecture under various equivalent formulations using LP Brunn Minkowski and LP Minkowski inequalities, but unfortunately, I don't have time to present this. I'll keep the point of view of the uniqueness question here. Another kind of comment is that maybe it's hard to see from this formulation, but actually this conjecture gets stronger and stronger as p decreases to 0. In other words, if you can solve this conjecture for p equals 1/4, then you can also solve it for p equals 1/2. Okay, and finally we stop at p equals 0 because beyond that there's no uniqueness. In fact, even at p equals 0, you can find two rectangles having appropriately chosen side lengths for which there's no uniqueness. Okay, so what is known about this conjecture? Well, Borodsky, Lutwak, and Zhang themselves have, and others later on, have shown that this is indeed true in the plane, but in dimension 3 and higher, this is general open. There have been many partial results in the positive directions regarding some particular cases. Unfortunately, I don't have time to go over these, but results by Colasanti, Lifshitz, Marsilietti, Rotem, Saroglu, and also in our work with Kolesnikov. Let me just mention that this result, which can be obtained by combining our work with Kolesnikov with the paper of Chen Huan Ling Liu, which together imply the uniqueness in the even LP Minkowski problem. In this problem, slightly below 1. So this is not science fiction. It's not true that the Brunn Minkowski theory stops at p equals 1. You can go below 1. And the only question now is how far can you go? Can you really reach 0? But our modest result was just to get it slightly below 1 minus a constant over n to the 3/2. And in fact, using some recent advancements on the KLS conjecture, not just some, but very, very dramatic advancement due to Yuanzi Chen, you can actually plug and play his estimates into our own and improve this to 1 minus essentially constant over n. Okay, so that's, I think, the best known general result for P, for general convex body. Okay, so of course I don't have time, but I think I still have a couple of more minutes. So what are some new results here? Our first kind of new result is say that if you have a smooth, if you have a C2 alpha smooth, strictly convex origin symmetric convex body, so that you can find a linear image of this guy whose curvature is pinched. So the principal radii of curvature are pinched between little r and capital R. Then the result is that you can give a positive answer to the uniqueness question of the for the even LP Minkowski problem, but for which range of p's? So you can go below 1. How far can you go? Of course, you're going to pay a price depending on the pinching constant, but the good news is that you get to multiply by dimension. It's actually not so bad. This is an equivalent formulation using one of those equivalent formulations that I alluded to. So this would be the corresponding LP Minkowski inequality with equality if and only if L is a dilated copy of K. Of course, the most interesting question is, when does this range include p equals 0? right? Because you want to hit zero, the conjectured value. So this happens if the pinching constant squared is at most something like the dimension over 6. That's pretty good, actually. And in this range, you get the uniqueness for the cone volume measure. So if you want, you can see this as an extension of the Brendle Choi Daskalopoulos result to self-similar solutions of the pinched anisotropic power-of-Gauss-curvature flow. Remember, their result was only in the isotropic case when the right-hand side is just a Lebesgue measure. So for K, which is a Euclidean ball, in fact, you can use ellipsoids. So comparing to their result, in their case, the pinching constants are just 1, right? So if we plug in 1 here into our estimate, you see that we can go, our estimate can go all the way down to something like minus n over 2, whereas the sharp result of Brendle Choi Daskalopoulos is minus n. So we cannot recover their sharp result, but we get it up to a factor of 2. And on the plus side, our result does hold for any pinched curvature. Yeah, in my last minute, this is my last slide. Another kind of thing that we can do is, while we unfortunately cannot resolve the conjecture in full, what we can do is resolve the conjecture if you allow us to modify the given convex body a little bit. So there are two natural distances for controlling the distance between two convex bodies. The first is called the geometric distance. This is just the best sandwiching constants for which you can sandwich one convex body inside two homothetic copies of the other body. And the other is called the Banach-Mazur distance, where it's exactly as before, only now you're also allowed to apply a linear transformation to one of the bodies. So our next result says that if you start with your favorite origin-symmetric convex body, and you denote by D its Banach-Mazur distance, the Euclidean ball, which by the celebrated theorem of Fritz-John we know is at most square root of the dimension, then for any perturbation parameter gamma, you can deform your body K bar into another body K tilde, whose distance from K bar is at most gamma, so that you have a positive answer to all these conjectures for P in this range. So of course you pay a price depending on gamma, depending on D, but again, the good news is that you get to multiply by the dimension. And again, when does this guy contain 0? Because we want to hit 0. This is the most interesting case. So you can hit 0 if the perturbation is of distance at most 8. So this means you can always perturb your body by a distance at most 8 and get a positive solution to this perturbed body of the log-Minkowski conjectures. So I call this the isomorphic resolution of the even log-Minkowski conjecture, isomorphic because this is in the same spirit of Boas-Klartag's isomorphic resolution of the slicing problem. Yeah, I'm out of time, so I'm sorry for going over. Thank you very much.